Okay. All right. So plan for today is just to do some major theorem stuff. Which, one second. Okay. Oh, that sounds weirder. Anyway, it's fine. It's okay. It's not a big deal. It's not a. It's more of a me problem than a people watching this problem. So the plan today is just to work through some major theorems. I'm at the point in studying where I've done so many problems that I feel like if I do more problems, I'll forget how to do old ones that I've learned how to do over the summer and before that. And also just there's a lot of stuff to know. So I did a handful of these on Twitch last night just because I wasn't feeling the being in front of a potentially large audience thing, just because the number of followers is way different. So I did like some metrization stuff uh, last night, and then I also did like Stone-Čech Compactification for the like fifth or sixth time live. So I'm going to start with Stone-Čech Compactification again. But I'm going to do it with a different type of thing just because I think it's really cool, and it's one of the things that's harder to wrap my mind around. But this version of it is going to be less categorical in nature. It's going to be more like set theoretic. So I'm just going to start with that. For context, if someone decides to watch this who hasn't seen these before, I am taking a PhD qualifying exam in topology in like less than 2 weeks at this point. It'll be a week from Monday is when the test is, and part of me doing videos on this channel and talking about math and talking about PhD experience, documenting that. And so it felt natural to do some of these problems on live instead of just being absent from the internet during the whole study session. So that's why I'm doing this here. And also, it's just a lot different because I can go into all the detail, which I would prefer to do usually, but it doesn't usually make sense to do that in like an explainer video that I would make on a similar topic. So uh, yeah, that's the idea. Um, that's there, that's there. Okay, cool. So I can see all the things, and I'm just gonna get started. So uh, this first thing is Stone-Čech compactification of discrete spaces. So there turns out to be like a really nice description of the Stone-Čech compactification in the case where your space is discrete. So this is, I've been labeling these with MT, MT, there we go. So Stone-Čech compactification of discrete spaces. So let D be a topological space. And let hello. Are you using mouse and tablet or just the tablet? So it depends. If I'm writing, I'm using a tablet, a Wacom. So so let D be a topological space, and let beta D be the set of all ultrafilters on D for each. Hey, how's it going? But are you using the mouse to pan the screen or draw lines and whatnot? Yeah, I'm using Yeah, one of these. And I'm doing everything with a pen. So this is a little bit maybe advanced for for having no topology background, but uh, I so like Stone-Čech Compactification, what I'm going to do right now, is something I didn't see until I was in grad school, and even like it was like I was told it was going to be on my PhD qual, and we didn't go over it in a class or anything, so I had to like figure this out on my own. Um, okay, so beta D is the set of all ultrafilters on D for each A a subset of D. Let A equal to the set of ultrafilters within beta D such that A is an element of the ultrafilter. So this is the collection of ultrafilters which contain A and let B equal to the set of those collections of ultrafilters such that A is a subset of D, be a base for topology. AT working out. Be a base for topology. Topology. So, so you have this set of stuff that's going to form the base of the topology, and the claim is that this is the Stone-Čech Compactification. So that just means that it has the unique extension property. So in particular, let E be a map from D into BD such that E of D is equal to the principal ultrafilter at D, which is just equal to the ultrafilter which contains the point D. Then beta D E is the Stone-Čech Compactification. So there's a few things to show in order to show that this is actually the Stone-Čech Compactification. And I can go over to this other version of it, which is way down here. Is it way down here? Yeah. Okay, so the Stone-Čech Compactification has this like extension property, which is that for every function into a compact Hausdorff space, there exists a unique beta f from the Stone-Čech Compactification to the compact Hausdorff space, such that when you compose the Stone-Čech map of the function with the embedding of the space map, you get the original function. In that sense, the Stone-Čech compactification extends functions to the entire compactification while still retaining the original value of the function. And of course, what do I want to say about this? No, that's all I wanted to say about this, right? So this is the extension property I need to check. So to do that, I'm going to just basically that's the end goal. So oh, okay. So proof. So note that, well, B, which is equal to this stuff, is actually a base for topology, is a base for topology as if, oh, how do I want to do this? It doesn't feel like the right way to do this. It's just I want to look at what happens. Oh, why this is insanely sad that I can't remember this most basic definition. Because what I have written down doesn't feel like the right way to do it. Yeah. Okay. Yes. Sure. Um, right. So as if D is within D, then ooh, the principal ultrafilter is within B, and the union of all of these principal ultrafilters is going to be, hold up. Do I want to say that? Do I want to say that? Instead of ultrafilters, the union of all those ultrafilters is going to be all of, oh, that's a weird thing to say. So this is a subset, okay, beta D is ultrafilters on D. So beta D is a subset of the power set of the power set. How do I want to do this? Let's see. I guess I need to be more particular, right? So if it's a base for topology as if U is an ultrafilter in beta D, then the empty set is not within. Well, like yeah, there's a set. That's not how I want to say it either. I just want to show that it, okay, well, if I intersect two things, start with that, because that's easier. So if A1 and A2 are within B, which are not empty, so A1 not equal, not equal to 8, oh, just notation. That's not equal to the empty set. Then if U is within the intersection of those two things, then this is equal to the set of ultrafilters within this collection of ultrafilters such that A1 is within the ultrafilter U, and A2 is within the ultrafilter U. So this is just, well, set of ultrafilters. So filters have a finite intersection property. So because both of those things are in there, then it's the set of ultrafilters such that A1 intersect A2 is within the ultrafilter, which is equal to the ultrafilter given by A1 intersect A2. And because they're ultrafilters, the proper ultrafilters, these intersections are not empty. So A1 intersect A2 does not equal the empty set. So this is actually within the base. So this implies that U is within A1 intersect, or there exists a third element in the base, which is this thing which contains the intersection. In fact, in this case, they're equal. So we're done with that part of it. And then next, I just need to show that they cover. That's the thing that was wrong before. I just need to show that they cover. That's all I need to do. That's the first thing. And then the second thing is that consider the union of a subset of D of these A's. Well, then by construction, every ultrafilter or on D contains a non-trivial subset subset A, subset of D, hence it will be in one of those things. So the union of a subset of D of A is a superset of, yeah, so if you are an ultrafilter in the collection of all ultrafilters, then you contain a non-trivial subset. So this union is a superset of all those possible ultrafilters, which is a superset of the union of subsets of itself. So that means that the union of all these things is just that whole collection. So we do have a base, hence is a base. That's the first thing. So now we have a base for topology. We can actually talk about the topology on these things, or start to work with it rather. So, and this is where we're going to start working with the extension property. So how much space do I have? Okay, I'll have room. I should have room. So now let f go from x to k be a continuous map and this should be D. D is my space. D is my discrete space. So let this be a map into continuous map into a compact Hausdorff space K. And define beta sub little f as a map from beta D onto the power set of the topology of K. Is that what I want? Yeah, because it's subsets of, yes, because I want to send an ultrafilter to another ultrafilter, essentially. So beta f of beta D to power set of the topology on K by beta sub f of an ultrafilter is going to be defined to be equal to f of that ultrafilter, which is equal to the set of just f of u such that u is within that ultrafilter. So this is at the least, right? So I don't know if f is onto. If f was onto, this would be a ultrafilter, but I don't know that because it's just a continuous map into a space. So it's a filter for it's a not a filter, it's a base for a filter. So note that for every ultrafilter within BD, beta f of u, that ultrafilter is a base for a filter. on. Okay, so by the axiom of choice, there exists, and how did I denote this? There exists an ultrafilter beta little f of u prime, an ultrafilter, which is, well, so yeah, this is going to be a superset of beta f of u, an ultrafilter, which is finer than beta f of u. So since this is going to be an ultrafilter in a compact space that converges to some point, so it's the same way that limits in compact spaces convert. Well, sequences in compact spaces have convergent subsequences. So ultrafilters in compact spaces have limit points, or filters in compact spaces have cluster points. So so we have an ultrafilter, it's finer, and it's in a compact space. So since beta f exists, beta prime is an ultrafilter on compact K, it converges say to I'm just going to do the notation for it. So beta f, this ultrafilter approaches some, and I'll call it K and then U, because it may be dependent on what ultrafilter you have. Thus, we define beta f of an ultrafilter to be equal to its corresponding limit. So it's going to be beta f, which goes from beta d to k. So that gives us this diagram. So you've got x, k, there's f, and then we have the embedding map, which was just from earlier, is just E goes to its principal filter. So that's what was stated as a supposition. And then you've got beta. I don't know why I'm doing X. It should be D. So we've got beta D, and now I've developed this map, beta F, and the goal is to show that that map is, or rather not that map, but I drew the arrow wrong. The goal is to show that this arrow here is just F, the E, and the doing E first and then doing beta F next is just F. So a few things is that, well, there's a few things I need to show, right? So I want to show that beta F agrees with F. So first off, let D within D, then E of D is equal to the principal filter, the principal ultrafilter at D. So this is the thing that converges to D. So beta F of UD is going to equal to just KUD, which is then going to be equal to, well, this is equal to the limit of the ultrafilter beta prime, right? So this is what beta subscript f of ud prime goes to, but this is equal to the completion of the coarser filter beta f of ud, and this coarser filter has a limit point at, or has a cluster point at yet beta f ud has a cluster point at f of d, since f of d is equal to a singleton fd, which is within the ultrafilter, or which is within this filter. So, and it's unique, right? It's a unique cluster point because the filter can't converge anywhere else. If it converged, if it had a cluster point anywhere else, then those two neighborhoods would trivially intersect, because if it had a cluster point anywhere else, it would have to be a singleton. Or I guess the other way to say that is that if it did have another cluster point, then neither of them would be cluster points. So that ultrafilter goes to f of d, which is then equal to, by definition, but that's just equal to, by definition of what the map does, KUD. So hence beta f of E of D is equal to f of D for every D within D. And that's, so the function beta f is extending the function f in the right way. So this arrow thing is doing what it's supposed to do. And then further, what else do I want to say about this? Yeah, so this just so that so beta f is the desired extension of f. Next, I need to show that, what do I need to show? As the extension property, I need to show it's compact. I mean, that shows that it is the Stone-Čech compactification. But I just need to make sure that, I would need to make sure that beta D is a compact space. Hold up. Okay. Okay. Oh, okay. That's what's missing. I need to show that beta F is continuous. That's the problem. Can I write this down? Let's double check. Be a topology space to be blah blah blah. Exists. Yeah. Okay. You just need beta F to be continuous. So this is a little bit involved. So now let U be an ultrafilter and the Stone-Čech in this proposed Stone-Čech compactification of D, and beta F of U be within V for some open subset of K. So this is just a continuity argument. So let's see. So use an ultrafilter. Beta F is going to be an ultrafilter. So since K is compact and T2, it is T4 and thus T3. So there exists a W within, hello. Okay, since K is compact in T2, it is T4 and thus T3. So there exists a W within tau K such that beta F of the ultrafilter is a subset of W, which is a subset of W closure, which is a subset of V. That's just a version of regularity. And so there is some pause. Since beta F of the ultrafilter corresponding to U goes to some value, which is just beta F of U. Then W, yeah, okay, yes, that's right, okay. So it converges to some value, that value is within, not subset of, is within W. So the ultrafilter, because filters are closed upwards, whatever the thing that it converges to, if you close up from that singleton, then W will be within that ultrafilter. So beta F of U prime. Ooh, so there is some A within U such that F of A is equal to, or rather is a subset of, because again, the function may not be onto, so F of A is a subset of W, which is a subset of W closure. So for any other ultrafilter, which I'm going to say, call it a weird V, within those ultrafilters that contain A, we have that F of A is going to be within beta F of, oh, is this what I wanted? Yes. Beta F, this font CV that I can probably recreate, not super well, which is then a subset of beta F of B prime, hence what I want to say. Yeah, so we have that F of A is within blah, blah, blah. So then beta F of whatever this ultrafilter that you construct from something that from one of these ultrafilters that contains A, it's going to converge to a point beta f of on CV that I wrote once and can't seem to do ever again. So it converges to that thing, which is then going to be a subset of f of A, which is going to be a subset of W, which is a subset of W bar, which is a subset of V. Hence, beta f of the cylinder A is going to be a subset of B as that ultrafilter within that cylinder with respect to A are all the collections. I say cylinder because that's what this notation means in symbolic dynamics, but this notation is the collection of all ultrafilters that contains A. Was arbitrary. So that is done, right? So thus beta f from beta d to k is a continuous extension of f such that beta f following e is equal to f. Hence, as f was arbitrary, beta d has the extension property and why is it compact? That's the issue. And why is it compact? Oh, that's gonna mess with me. So hmm, here's for topology in particular. Okay, so we have subsets of D. All of the singletons of D are going to go to different places. Oh, I don't like this. This is gonna bother me now. So at least, okay, I'm gonna call it the Stone-Čech Compactification, and I'm gonna move on because that's not it's not what I need to focus on right now. But there's like a big question of like, why is this thing compact? So it is this is a continuous extension of f such that this blah blah blah, and hence arbitrary. So beta d is the extension property and is the Stone-Čech Compactification. I'm gonna do like a big like thing here because I am confused. The previous stuff is fine. And I know that the like Stone-Čech compactification of a discrete space has a Clopin basis, which means it's zero dimensional. And zero dimensional spaces I don't think are always compact. Yeah, that doesn't make sense. It's just false. Yeah. Hmm. This feels weird. Stone-Čech of a discrete space is compact. Okay. Do this principle associated filter with that, blah blah blah. The set of ultrafilters. Why is the set of ultrafilters a compact? Why is it compact Hausdorff? Why is the set ultrafilters? Right. Oh. Hmm. Okay. So I'm gonna do it. I'm gonna try to do it. Um, so the red part is as long as it's compact, because that's not clear at all. So as long as it's compact. So, okay, so how does this work? Suppose not. Suppose not. Then there exists a collection of open sets. So there exists an open cover U, a subset. Oh, I'm gonna use a different letter, or just make it fancier. That's not what we wanted. That was worse. That's also not great. Let's just call it W, because ultrafilters will be the fancy use. So W, an open cover of beta D such that W has no finite subcover. In particular, in particular, we may assume that for every W within the open cover, W is equal to some principal, some basic filter. Because every, so a union, how does this work? So this is because since the basis is Clopin, is that what I want to say? Because it's every, I don't want to say that either. It's just that every open set is a union of those things, but the union of those things determines a new set in the space, right? So that uh, is W is equal to the union of some of these things. So I'm going to say I within I, which is equal to the set of ultrafilters within beta D, such that AI there exists an AI, there exists an I such that AI is within. There exists an I within I such that AI is within the ultrafilter. But that's just equal to Well, that means that the union over all I with an I of AI is within the ultrafilter, which is equal to just the cylinder of the union. And that's a subset of, and that union is a subset of D. So I can just replace W with each W within W. Oh, that's gonna get gross. Let's make it fancier, right? Just hard edges for the open cover, soft edges for set in. Okay, that's fine. So then, since no finite subset of W covers beta D, then no finite subset, so you can form, how do you do this? It's just that the union of these makes bigger and bigger stuff, but they never in a finite amount of time. So then letting hard edges, W equal to the set of WA, I with an I, AI, a subset of D, then the AI complements. So if I look at AI complement, then consider AI complement I with an I. This is a subset of the power set of D. Then if I intersect any two of them, intersect another one, J complement, this is just going to be equal to De Morgan's laws, AI union AJ complement. So this is going to be equal to, or this is going to map to, oh yeah, okay, so this is non-empty since the union of the WAI, yeah, so WAI union WAJ. AI union WAJ does not equal to the empty set. Because AI and AJ are not empty. This is just equal to, this is just going to be equal to AI union AJ, that cylinder. And so since AI and AJ do not equal the empty set, this is equal to the union of those filters, which is not equal to the empty set, so their complement is also not empty. Or in particular, that's not what I want. I want that it's the union of those two things don't equal all. It's not equal all of the ultrafilters on the. So there's a set that it misses, right? So this complement is not equal to the empty set. Okay, cool. Right, so AI union AJ complement is not within there. So further, so since for every I and j within I, AI intersect AJ, or AI complement intersect AJ complement does not equal the empty set, and as AI does not equal the empty set for every I with an I, AI complement does not equal the empty set for every I with an I. This collection of complements, this collection forms a base for a filter. So by a C, there's the axiom of choice, rather. So by the axiom of choice, there exists. Yeah, so by axiom of choice, it generates an ultrafilter. Or it may be extended. Yeah, it generates, I'm going to say it generates an ultrafilter. Or no, I'm going to say it generates a filter, which then may be extended to an ultrafilter. Yet the resulting ultrafilter which I'll call U prime, which contains with U prime a superset of AI complement such that I is with an I, is not covered. Or is such that U prime is not within the union I with an I of the W I's, right? Or just, yeah, union over the open cover. Which is equal to the union over I with an I of the W AIs. But that's a contradiction, because that is supposed to be equal to the whole space. Yeah. Yep. Hence, beta D is, in fact, a compactification of D with the extension property And thus is the Stone-Čech compactification. Up to equivalence. Okay. Boom. Did the thing. Oh, and I don't, that's sad. I'm not gonna be able to fill that space. I guess I could do the Clopen base one. I can do the Clopen base proof with the little bit that's left. So, also, I don't know why I chose to write that in Baker Miller pink adjacent color. Just the it's rage inducing. So, okay. So I'm gonna do that next thing. So it is helpful to note that beta D is zero dimensional. If D is discrete. So in particular, which is kind of weird to think about. It's a discrete, or it's a zero-dimensional compact space, which could have a lot of things in it. Yeah, it's weird. So beta D is zero dimensional if D is discrete. That is, if A is within the basis, then A complement is equal to the set of all ultrafilters within beta D, such that A is within, or A is not within U, but since U is a ultrafilter, or however, BG is a set of ultrafilters. A not within U implies that A complement is within U. So it's equal to these ultrafilters as before, which implies that this is just these guys. But that's just equal to A complement, which is within the base as well. Hence, beta has a Clopen base. Or beta is Clopen. Base for beta D, and thus beta D is zero dimensional. Okay, solid. Oh, 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 oh. That wasn't terrible. This part, this pink thing, is gonna throw me off every time. But so that's Stone-Čech compactification of a discrete space in terms of ultrafilters. The next thing I want to do is a little bit more involved. Do I have time to do this? I do have to be somewhere in a second, so it was just like kind of sad because I just did one thing. It's been like an hour. You know, it might be a good place to cut it, which is so I didn't get to do as much stuff as I thought I would, which is okay. But I think I'm gonna cut it there just because that was pretty involved. I learned something and I have to do some other things today, so I'm gonna hop off. Also, regarding this poll that I put out, just because I was having fun with it, I just like was like, oh, I'll just put a poll on it, just to see what happens. Turns out that like Chrome-based browsers, like Opera, which is what I use in well Chrome, doesn't have the imposter syndrome emoji. So like if you look at this poll that I did, right? It just like shows up as like Unicode box. And when I put this out last night, the first 10 votes were for the imposter syndrome emoji. And so I was very confused. I was very confused because I was like, why is everyone voting for the imposter syndrome emoji? Um, but it's just because it doesn't show up, I guess. But I was like, what is going on? Because this is what it shows up on like on an Apple device, right? It's just I don't know if I could. Oh, this is not a good idea. You know what? I'll just if I cut this out and clip it, I will just put it in post. I'll put the actual what it looks like. But the Unicode box was the imposter syndrome emoji, which was just pretty funny to look at when it first came out, and the first 10 people to vote on it just picked the imposter syndrome emoji. But uh, aside from that little thing, nothing else is going on other than I'm still ahead in a book. I've got less than 2 weeks to do this. And yeah, I'm just gonna leave it at that. I will see you soonish, I guess. I'll be around the internet. I'll keep up with it. But I probably won't be doing stuff next week. I might do something this weekend, but next week and up until my test day, which is gonna be the 22nd, I'm not gonna do much on the internet, if anything at all. Or if I am somewhere, it's gonna be like on Twitch, doing uh, stuff and doing it in a lower pressure scenario. So that's that. Um, oh, and I just lost chat, so okay, yeah, it's good. No one said anything. That's okay. So anyway, I'll see you later.